Howdy, folks. Let's go ahead and take a look at number 46 through 50. They tell us the strength of a fishing line is proportional to the cross-sectional area. So weight is proportional, the weight it supports, or the strength, force. So F or S is proportional to the cross-sectional area. Okay, so they say a 17-inch long fish broke a fishing line that is 0.015 inches in diameter, and they want us to find out how much of a diameter are we going to need in our second line if we're trying to catch a 25-inch fish. Well, again, strength of this is the amount of force the string can take. So what they're telling us is that the weight is proportional to the area. Well, what is the weight? Well, that's the weight of the fish. Now, the weight of a fish, that's mass times the acceleration due to gravity, and mass is really density times volume times gravity. So just as a rehash, here, what they're really telling us is, all right, the weight of the fish is essentially the length cubed, 17 cubed, okay? And that is going to be tolerated by a line that is 0.15 inches in diameter. So here, whether we're doing radius or diameter doesn't really matter because that conversion factor will cancel out in the comparison. So as long as both of these are diameters, I'm just going to use those numbers. Okay, so the first area is going to be the diameter squared. I know that we would cut it by 2, squared and multiply by 5, but again, those are going to cancel out. Okay, so what are we getting? 17 cubed over 0.015 quantity squared. All of that is going to equal the 25-inch cubed all over the new diameter quantity squared. Okay, now in this case, I happen to set it up upside down, but we can flip the whole fraction over. 0.015 squared over 17 cubed equals d squared all over 25 cubed. Okay, and again, the idea was that the strength or the weight is proportional to cross-sectional area. We've seen that they're never going to give us the weight and usually neither the density, but we need to remember that weight is proportional to length cubed. Area is proportional to length or radius squared. Okay, so they give us two sets of numbers, the length of the fish and the radius or diameter of the fishing line. So there we go. All right, 47. The number of transistors on a chip has been growing exponentially since 1990, and they want us to predict how many transistors we're going to need in 2025. So because they're telling us that it's growing exponentially, they're already telling you this is not linear growth. That means that you cannot just put the numbers into the stat register and do linear regression. Well, what do? Well, we need to match the growths of these numbers. So just really quickly, if I'm plotting the numbers, like x, and then this is e to the x, we're going to see something like this. But to be able to get an accurate prediction, we need to linearize the data so that we can just do linear regression. How do we do that? Big numbers are proportional to log of the number. So what are we going to do here? The first number I put in is 10 to the 6. Then I push log. Then I type in, after you push log, the calculator will be ready for the next number, so you do not need to press enter. So again, I would do 10 to the 6 log. 1990, sigma plus. Then I'm get ready for the next number, 10 to the 8. Then I push log. Then I do 2002, sigma plus. Then I do the next guy, 2.6 times 10 to the 9. I take log of that. Then I type in 2011, sigma plus. And then the last number, 5.2 times 10 to the 10. Then I take log of that number. Then I type in 2020, and I do sigma plus. Now, in this case, You can do it through the years, or you can really do it. This would be year 0. This would be year 12. This would be year, let's see here, 21. And this would be year 30. So I really think you should do it that way. So again, 10 to the 6 log 0 sigma plus. 10 to the 8 log 12 sigma plus. 2.6, 10 to the 89 log 21 sigma plus. Now, when you do this part for 2025, that's going to be 35 years. So when you do the regression and you ask for the y value, you're going to have to cancel the logging that it's doing in the calculator. Remember that all these numbers were logged when we put them into the calculator. And so the calculator does the regression with the logged version of those numbers. So then we need to unlog them. So the last thing we do is we raise that number 10 to the y. And that's our actual answer here. Okay. Number 48, thankfully, is a solver. You throw that into your solver and it gives you an answer. It's going to be in radians, so make sure that your calculator is set to radian mode when you answer that one. All right, 49. They tell us that the pyramid volume, which, we don't know the pyramid volume, but we do know that the corners of the pyramid reach the ends of the cone here. And this height right here, x, this is really x. And this height right here would be 13.2 minus x. All right, well, part of the challenge here is that we need to relate the radius and the side length through here. All right, so what do we know? We know that the corners of the pyramid touch the rim of the cone. So what we can say is that the diagonal, D, is equal to the diameter. Let me actually go work off onto the other space. So right now we are saying that the diagonal is equal to the diameter. That's because we happen to have a circle and then the square reaches through here. Side, side, square root of 2 times the side is the diagonal. Okay? So, in this case, the volume of the cylinder equals the volume of the cone. Let's start loading it in. So then that's pi times the radius. I'm just going to call that diameter over 2 quantity squared times the height of the cone. Sorry, I was saying cylinder, but the height of the cone is going to be 13.2 minus x. And that volume of the cone is going to equal the volume of the pyramid. Now the volume of the pyramid is going to be the side squared times the height. And there's technically a 1/3. I apologize. I forgot 1/3. I apologize. I wrote 1/2. 1/3. And so there's a 1/3 side squared times the height, which we are calling x. Alrighty. So the challenge here is that we need to, again, talk about the side length and the diameter. Well, don't forget the diagonal is square root of 2 times the side length. And all of that is going to equal the diameter. So putting all this together, we get 1/3 pi diameter over 2 squared times 13.2 minus x equals 1/3. And the side here, if we solve for the side length is going to be the diameter divided by square root of 2. Okay, so I'm going to put that in here. That's going to be diameter over square root of 2. And then that quantity gets squared times x. All of that, right? We just throw that into our solver. So we're going to solve for x. The tricky part here is recognizing that the diagonal is the diameter, and once you have a relation between by that, you can say that the diameter divided by square root of 2 is the side length. Okay, alrighty. Let's go ahead and take a look at number 50. Number 50 is having us get a length in 3 dimensions. Now, if I'm getting a length in 2 dimensions, I do a squared plus b squared square rooted. Well, if I'm doing it in 3 dimensions, turns out that it's going to be a squared plus b squared plus c squared. All of that is going to give us the length of that diagonal squared. Okay, so let's see here. How far are we going in every direction? Well, part of the challenge is we're going to go to the midpoint of this shape, and then we're going to go up all that height. So we're going to have to be careful. So the first distance we're going to go is going to be half of 28.2. The next distance we're going to go is going to be half of 17.4. Then we're going to go up in this distance, 42.6. And lastly, we need this height here for our pyramid. So how do we get that height? Well, it turns out we're going to need to do another Pythagorean theorem with this. Golly, this test is so elaborate and tedious. So how do we do that? You do the Pythagorean theorem with 28.2 squared and 17.4 squared. And when you square root those, after adding them, we get 33.6. So this diagonal here is 33.6. But we're really working with half that distance and this height here to get that length here. So what we need to do then is cut it in half to get half that diagonal, and that's 16.8 right here. So lastly, we have 25.3 squared equals 16.8 squared plus h squared. And when we solve for that number, we find out that the height of this is 25. Okay, so putting all this together, it's a super Pythagorean theorem, as I like to call it. And it's going to be 28.2 or 14.1 cut in half squared plus the 17.4 cut in half quantity squared, right? Because we're going here and then here, plus the 42.6. And to that 42.6, we're going to add that height of the pyramid right here, which we found out to be 25. And then you square each of those numbers, you add them, and then you square root them, and there's your answer. Alrighty, folks, thank you for that one.